guys, I'm Rachel Reed, and this is my video lab report for Lab 2, the motion of a falling object.
In this video, we will talk about the momentum principle as it pertains to falling objects, investigate this principle in real life by using tracker analysis on a video of a falling object, and then, using the data collected from our tracker analysis, we will create two computer models describing the object's motion. One model will assume the net force acting on the ball is in the y direction consists only of gravity. The other will include the drag force as part of the model. Finally, we will compare observed tracker data with the data collected from our two models and discuss why the data is so different.
Before we can start this lab, we need to discuss the momentum principle. The momentum principle states that the rate of change of momentum is equal to applied force, or that change in momentum equals net force plus change in time, or taking into account that momentum equals mass times velocity, that final velocity equals initial velocity plus net force over mass multiplied by change in time. Basically, it just means all forces must be totaled together to describe the momentum or velocity changes of a system. Since in this lab we are dealing with falling objects, there are two forces we need to take note of. The first is weight or gravitational force, which is described by the equation weight equals the negative mass of an object multiplied by the gravitational constant, which in this lab we assume to be 9.8 meters per second squared. The second force acting upon a falling object is drag force, which acts in the opposite direction of relative motion of any object moving through a surrounding fluid, i.e. water or air, and in this experiment we will describe using the equation drag force equals negative drag coefficient multiplied by velocity squared. Now that we have reviewed this information, we can proceed with the lab. Here is our video and tracker. We can see we're analyzing this video from the moment the object is released to right before the object hits the ground. Tracker gives us a variety of data, however, we will only need the time values and the y values for this experiment. From the graph tracker gives us, we can see that it appears our object is experiencing acceleration or a positive change in momentum, as with every time interval, the distance between the object's previous position and its new one grows by a larger amount. Now we will create our computer models, and to do this we will need the object's initial time and y values, as well as its final time values.
Let's briefly go over the code for our models. In both models, we set the ball's mass to an estimated value of 0.13 kilograms. We also start the models at the initial y position value that we found in our observations, and set the initial velocity equal to a zero vector. In both, we also use Newton's second law to update velocity and position values. The difference between the two models comes down to how we calculate our F-net value. In the model that is only gravity acting upon the object, we set F-net equal to the weight or gravitational force only, and in the model where drag is included, we set F-net equal to our weight plus our drag force. Now, when we run our model for gravity only in Python, we can see that our model is different from what we observed because our modeled object appears to go past the origin and ends up at a negative y position value, which didn't happen in our observations. When we run our model for drag, we get a graph much closer to what we observed.
Now that we have created our code, we can compare our observational and our model data. We can see that though our model, which only included the force of gravity, may have started out lining up with our observations, it grew farther and farther away from our observational data with time, and shows the object to fall at a much faster rate. We can also see that though our model with drag is closer to our observational data and ends up at the same position value of our observational data, it doesn't have the same slope as our observational data, and many of the values are different. So what accounts for this difference?
In our model without drag, the difference between our modeled and observed data can be accounted for due to the fact that an important component of our net force was not included, aka the drag. But what accounts for the difference in our model with drag? Well, when we were designing our model, some of our values had to be estimated. The first was the object's mass, which could not be obtained as we did not have a scale precise enough to find the mass. The second was the drag coefficient, which due to the complex shape of our object, we could not know precisely. These could have had an effect on our velocity and position values as the experiment went on. There were also issues with the initial setup of the experiment as the lemur tilted while falling, changing the drag coefficient at different time intervals as it fell. Okay, now to answer final questions. To understand the first question, we have to know what terminal velocity means. Terminal velocity occurs when an object ceases to accelerate and continues to fall at a constant speed. Neither of our models predicts terminal velocity. The one for gravity only doesn't, as in that model, no force works against gravity to slow the object to move at a constant pace or speed. And so the velocity just continues to increase as the object falls through the air. The model with drag doesn't, as it doesn't run for a long enough time for the object to reach terminal speed and for velocity to be constant, though it was heading that way, and if it had run for longer, it would have reached terminal velocity. To answer the second question, I ran the model with an initial velocity equal to a 0 vector and let it reach terminal velocity, and did the same with the initial velocity equal to 1 in the y position, and as we can see from the following graph, eventually both reach the same constant velocity value, and thus it doesn't matter if a force is initially applied to the object or not.